The condenser is positioned at the top of the column. It cools and condenses the vapor into liquid, which is then collected as the distillate. The condenser helps in maintaining the reflux ratio, which is essential for the efficiency of the separation process. The reboiler is located at the bottom of the distillation column. It provides the necessary heat to generate vapor from the liquid mixture, driving the separation process. The reboiler ensures that the heavier components remain in the liquid phase, while the lighter components vaporize and rise through the column. The reflux drum, also known as accumulator, is situated downstream of the condenser. It collects the condensed distillate and separates it into two streams. One that is returned to the column as reflux to enhance separation efficiency, and another that is taken off as a distillate product. The reflux drum plays a vital role in maintaining the balance and control of the distillation process. Other important equipment includes heat exchangers used for preheating the feed and cooling the distillate. The other one is control valves, regulate the flow rates of the liquids and vapors. And the last one is pumps. It is integral to the operation of a distillation column. They are used to circulate the liquid between the column and the reboiler, and between the column and the condenser. Pumps ensures that the liquid levels and flow rates are maintained at optimal levels, supporting the continuous operation of the column. Our distillation column is designed to separate a mixture of 8 components: ethane, propane, isobutane, cisbutane, ipentane, isoprene, cyclohexane, and toluene. This mixture presents a challenging separation task due to the varying volatilities of the component. The column configuration includes a total of 21 stages. These stages are divided into two sections: 13 stages in the stripping section and 8 stages in the enriching section. This configuration is designed to optimize the separation efficiency of the components. Key dimensions of the columns are as follows. The column height is 15.4 meters with a diameter of 2.4478 meters and a thickness of 19.93 millimeters, while the cross-sectional area at the top of the column is 4.773 square meters. Additionally, the cap radius and cap height are both 1.2239 meters, ensuring adequate space for vapor-liquid contact. Internal configurations of the column include a downcomer area of 0.565 square meters, which is 12% of the cross-sectional area. The downcomer chord length is 2.173 meters, with a segment height of 0.665 meters and a downcomer panel height of 0.3 meters. The net area is 4.141 square meters, while the active area is 3.576 square meters. The area of one hole in the trace is 0.00001963 square meters, with a plate thickness of 5 millimeters, and the trace spacing is zero point 0.6 meters, and the hole diameter is 5 millimeters, and there are total of 18,220 holes. The column operates under specific conditions to achieve the desired separation. The feed flow rate is 100 kmol per hour, with a distillate flow rate of 44.7097 kmol per hour, and a bottom flow rate of 55.2903 kmol per hour. The operating pressure is maintained at 1.43 Newton per square millimeter pressure unit to ensure optimal separation of the components. Economic consideration for this distillation column include capital costs, operational costs, and profitability. Capital costs encompass the cost of construction materials, fabrication, and installation. Operational costs cover energy consumption for reboiling and condensing, maintenance, and labor. Profitability is influenced by the product yield, with a higher purity and recovery rates increasing the value of the products. Additionally, the variability in the market prices of feedstock and products impacts the economic feasibility of the operation. To enhance the performance of the distillation column, several potential improvements and future work areas can be considered. First, optimizing the number of stages in the enriching and stripping sections can improve separation efficiency. Implementing heat integration techniques such as reboiler and condenser heat recovery can significantly reduce the energy consumption. Utilizing advanced process control systems will allow for more precise operation, leading to increased efficiency and product quality. Exploring advanced materials for construction can offer better resistance to corrosion and pressure, potentially lowering long-term maintenance costs. Conducting detailed process simulation using a software like Aspen HYSYS or CAMCAD can refine design parameters and validate performance. Investigating the use of different types of trays or packing materials can enhance mass transfer efficiency. Finally, designing the column for scalability and flexibility to handle variation in feed composition and flow rates will accommodate future process expansion or changes.
In conclusion, designing a multi-component distillation or MCD system is a long complex process that requires in-depth knowledge of thermodynamics, fluid dynamics, and process control. Vapor-liquid equilibrium also plays a great role in determining the separation efficiency of the components. Then the greatest dilemma usually encountered on is data mining due to its name being analogous. Some components are mistakenly recorded, just like what we did as well in our, and we took numerous retakes on how we obtained our datas. Then what surprises me the most is that chemical and mechanical engineering calculations are harmonized in the MCD because they address complementary aspects in the of the design and operation. So chemical engineering or our course focuses on the chemical and thermodynamic aspects of the process, while in the mechanical engineering ensures that physical robustness and safe operation of the equipment, and then altogether, they ensure that MCD systems are efficient, reliable, and safe, capable of producing high purity products with minimal energy consumption and operational risk. Here are some of the references that we used in designing our distillation column. That's all for our proposal. Thank you so much and have a great day, sir.